So we've got the measurement problem and realism and instrumentalism on the table. So I have the sense that Hugh Everett is somewhat of a character, and and he didn't really have a classical physics career or career as a physicist. So just who was he before we get into his deep insight?
Sure. I mean, I should be honest that I'm not the kind of philosopher who's done a very deep study of the historical figures, so my grasp of Everett's kind of surface, but I can give you the highlights. So Everett was a grad student of John Wheeler. Wheeler is a very eminent post-war physicist, worked on the Manhattan Project, moved into general relativity, was kind of an eminence grise of American physics for a very long time. Everett was his grad student, I think in Princeton around the mid to late 50s. And he was interested, among other things, in this measurement problem we're talking about. And to translate really anachronistically the way I described the measurement problem a minute ago, what Everett asked was, is it really the case that we know that we don't see cats alive and dead at the same time? And that's a set of ideas that led him to thinking about what was actually going on physically in the process of measurement. How do you model measurement inside quantum mechanics? And I'm sure we'll come back to what that involved, but just to close the brackets on his own story, he had a pretty rough ride with this set of ideas from Wheeler. Wheeler wanted him to go and talk to Niels Bohr in Copenhagen, who's one of the founding fathers of quantum mechanics. Wheeler wanted Everett to make sure that Bohr was okay with his ideas. Bohr was not okay with his ideas. Wheeler put a lot of pressure on Everett to really censor an awful lot of the material that went into Everett's published dissertation and the paper that came out of it. I mean, if you think academia has a conformity problem now, you ain't seen nothing yet. Have a look at physics in America in the 1950s. So it's certainly true that Everett's ideas got very heavily, suppressed is too strong, but a lot of the pieces of them were suppressed, and what was publicly communicated was much smaller than Everett's original set of ideas. And in fact, we only really got clarity on what Everett himself wanted, nearly 50 years later, when a lot of his papers became available. Everett then left physics, and the obvious way you tell this narrative is that Everett was driven out of physics by the fact his ideas were not taken seriously enough. I'm not at all convinced that was actually true. I mean, what Everett went off and did was work in, I think, the Rand Corporation, some of the kind of military-industrial complex that was growing up in the Cold War. They wanted scientists. They wanted people with Everett's technical skills. They paid pretty well. Everett was interested in that stuff as well. I mean, he had a bunch of different things that interested him. I think the story as to why he actually decided to leave academic physics and go and work for Rand is kind of complicated and multifaceted. But anyway, he then basically spent about 30 years in that work. He was, it would be unkind, but not completely unfair to say that his research was largely focused on how to maximize casualties from nuclear attacks. Maximize, you understand, how we can best deploy our own nuclear weapons to maximize the other side's casualties. He was very involved in that kind of thing. My sense of exactly what he was doing there is kind of vague. Frankly, I assume a lot of it's still classified. He certainly had a very colourful and difficult personal life, the details of which, frankly, are messy enough that I don't know them well enough that I don't want to accidentally overstate or pass on rumours. There are plenty of sources for this kind of thing, but certainly he had significant substance problems. He died quite early. He had major health issues, and he died sometime in the 80s, I think.
Well, this censorship you mentioned, I noticed already in the book, at the beginning of your book, the Emergent Multiverse, which I'll name it, of course, in the introduction, but it's the Emergent Multiverse, quantum theory according to the Everett interpretation. The epigraph is a little bit that was cut from his thesis at the urging of Wheeler. And while you were talking, I pulled it up, and maybe, I mean, we don't have to talk about it right now, but maybe I'll just read it just so people can get a sense of how he wrote, because he was a nice writer. So okay, what he wrote was, we have then a theory which is objectively causal and continuous, while at the same time subjectively probabilistic and discontinuous. It can lay claim to a certain completeness, since it applies to all systems of whatever size and is still capable of explaining the appearance of the macroscopic world. The price, however, is the abandonment of the concept of the uniqueness of the observer, with its somewhat disconcerting philosophical implications. And one thing that those three, just as three sentences, it's quite powerful. There's a lot there. But also I have the sense that his thesis was quite short, quite to the point, and then he just basically left physics. Oh, well,
I think that's right. I mean, there's almost a sort of mic drop aspect about it.
Yeah, exactly. But okay, cool. Well, this leads us to what you bracketed this, what his major insight that led to this new quantum theory, the many worlds or Everett interpretation or theory. Actually, I mean, since we've been jumping around a bit, I should also ask how you feel. I mean, you write about this a little bit in the Emergent Multiverse, but how you feel about the term interpretation or theory, because I mean, as Tim Modlin has stressed to me, they are different theories. Like Bohmian pilot wave theory is a different theory from many worlds. In the many worlds theory, I almost said interpretation. They are not merely different interpretations. So this, I think, leads to a lot of confusion in the lay population.
Yeah. So it's a little subtle, and I half agree with Tim. So what I'd say is we've got a theory, or at least the formalism that's the core of a theory, in what I'd call unitary quantum mechanics. And that's the physical theory that physicists are in practice using to calculate. And though that's the kind of thing you learn as a student, is the kind of thing you work with if you're a professional physicist doing calculations in quantum mechanics. The kind of default interpretation of that theory is the kind of ad hoc mess I was talking about earlier. Now, you can then distinguish between what I'd call pure interpretations, which leave the mathematical formalism of the theory alone and tell you how to make sense of it, versus new theories. To go back to my framework earlier, if I have a change the philosophy way of solving the measurement problem, I'm probably leaving the formalism of quantum mechanics alone and just trying to make sense of it. If I have to change the physics approach to quantum mechanics, I'm going to be genuinely using a different theory with different equations and different calculational content. So in that sense, I certainly agree with Tim that, with Maudlin, I mean, that the de Broglie theory is a different theory from the many worlds theory. I'm less keen on saying that the many worlds theory is a different theory than, I don't know, orthodox textbook quantum mechanics, rather than a different interpretation of the same underlying mathematical structure. Now, Tim, among other things, individuates theories significantly more finely than I've just done. And Tim would also want to say that we can't make sense of the framework, which is exactly what forces us to change it. But then those are substantive philosophical points on which people can differ. But I think there is an important distinction between those approaches to quantum mechanics that effectively require us to do new physics, to change the theory, at least the way physicists individuate theories, and those approaches that don't require us to do that. And I tend to use the word interpretation to cover the latter ones. That's why I tend to talk about the many worlds interpretation, the Everett interpretation, more than the many worlds theory. And I should say a lot of the reason why I'm attracted to that kind of way of doing things is that I think changing our physics is kind of hard. And the de Broglie theory is a very nice toy model to explain a few very simple quantum things, but we're many, many decades behind the current stage of empirical success of physics.
Mm-hmm. Yeah, that's my quite limited understanding as well. So thank you for, again, entertaining a tangential question. But let's go back to Everett and his thesis and this new insight.
Okay. So here's the thing. The way I set the problem up earlier, I was saying, well, look, changing the physics is difficult, changing the philosophy is difficult, but it looks like we have to do one or the other because the theory by itself, taken realistically, says cats are alive and dead at the same time. And when we look at cats, they're clearly not alive and dead at the same time. Well, Everett effectively asked, he didn't use the cat as the example. I don't think Schrodinger's cat was a famous example for a while longer, but he effectively asked, well, what would it actually look like if you saw a cat that's alive and dead at the same time? And I think intuitively it would kind of look like a fuzzy cat, like you're seeing double, or you'd have way too much to drink or something. But intuition isn't a great way to work out what would happen in a scientific experiment. If you ask the theory what happened if I look at a cat that's alive and dead at the same time, well, the theory says if I look at a cat that's alive, then I will have to go into some physical state that records my observing the cat as alive. I have some neurological state in which seeing the cat as alive is encoded in my memory and cognitive processing. And there's a different state I'll go into if I see a dead cat, where my neurological state is different, my neurons are fired differently, maybe what I've written down on my lab notebook is different, if you want to be less psychologized about it. So in that case, given the mathematics of the theory, slightly technical level, given it's a linear theory, then if the cat's alive and dead at the same time, and I look at it, then I go into a seeing the cat alive and a seeing the cat dead state at the same time. I don't go into some third state that you could call seeing a weird cat. I mean, again, there's a perfectly plausible neurological state I could go into where somehow I'm seeing a fuzzy superimposition of two cats. But quantum mechanics doesn't predict I go into that state. It predicts that I, at the same time, go into the seeing a live cat state and the seeing the dead cat state. And it's all correlated. So that me and the cat, at the same time, go into the cat's alive, I see cat alive state, and the cat's dead, I see cat dead state. And if I tell you about it, then you and me and the cat are now in a cat alive, David sees cat alive, David tells you the cat's alive, plus cat's dead, David sees cat dead, David tells you the cat's dead state. And if you then announce the result on the podcast, then all your audience go into, at the same time, hearing that the cat's alive and hearing the cat's dead. And again, all of this is correlated. So the whole of the planet, pretty quickly, is at the same time doing two separate things. It's doing a as if the cat was alive thing, and it's doing a if the cat's dead, as if the cat was dead thing. And both those processes by themselves are ordinary and mundane and just describable in classical everyday terms. And they don't interfere with each other. In quantum mechanics for microscopic systems, the whole reason we have to say things are doing two things at the same time is they have a weird thing called interference, which is kind of like the particle being there affects the particle being here and vice versa. But for well understood dynamics reasons, that interference goes away when things are big enough. So really, the live cat goings on and the dead cat goings on are completely independent of each other. And what does it mean to say, well, physical reality is instantiating two completely different processes, a live cat process and a dead cat process? Well, it means there are two chunks of physical reality. There's a live cat chunk of physical reality and a dead cat chunk of physical reality. And so in slightly picturesque terms, there are two worlds. And the experiment calls the world to split. Initially it calls the cat to split, then it calls me to split, then it calls you to split. And really the processes that are causing the splitting aren't us talking, they're going out much faster than that. And so the idea is that the theory, it's not that Everett's idea wasn't that we could introduce parallel worlds to solve the measurement problem. That would be a kind of change the physics strategy in a kind of weird one. Everett's insight was if you look carefully enough at the physics we already have, you'll see it's a parallel universe theory all along. It's helpful to think that these aren't universes in some kind of fundamental sense. So, David Lewis, the philosopher, talks about possible worlds as sort of concrete, actual different worlds out there. But those are exact, they're fundamental, they're in the deepest structure of reality. These aren't worlds in that sense. They're worlds in the same way that planets are worlds. So Earth and Mars are worlds. Why? Because Earth and Mars don't interact with each other very much. Well, stuff on the surface of the Earth and stuff on the surface of Mars basically leave each other alone until someone sends a space probe. Mars is a robust, self-contained system, so is Earth. But there's no exact blocking of interaction between Earth and Mars. There's no exact moment where you leave the atmosphere of Mars and go into interplanetary space and reach Earth. You certainly won't find Earth and Mars in our fundamental physics. They're emergent ontology, emergent stuff. And the claim in the many worlds theory and the Everett interpretation is if you look carefully at the mathematics of quantum mechanics, you'll find that kind of multiple worlds is just built into the way the theory in fact evolves. So the idea is that you haven't changed the physics, and in some sense you haven't changed the philosophy either, because this is still a third-personal realist account of what's going on. You've just got whatever it calls this disconcerting implications. You've got lots and lots and lots of other versions of me out there in physical reality.
So again, just to recapitulate, to make sure that I'm on the same page, where we began with the measurement problem arises quite basically from things doing multiple things at one time, which diverges from our classical picture of the world. And the way that Everett explains this, his insight, is that each of these different things happening at the microscopic level corresponds to a different world, but it's not an ad hoc addition. It's what follows from the physics of the theory.
So that's nearly right. It's often what you'll see in popularizations of it. From a philosophy point of view, it's not quite right because what's justifying this language of worlds is that I've got sort of separate autonomous chunks of reality doing their own thing and not interfering with each other. That means that the world language can't be extrapolated all the way into the microscopic. So if I've really just got an electron that's here and there at the same time, I don't really have any good grounds, I mean, other than maybe metaphor, to say, well, that means there are two worlds, an electron here world and an electron there world, because the electron here and the electron there they're not separate strands of reality. They're interfering with each other in the jargon of quantum mechanics. They're not decohering in that jargon. The point to which we're allowed to really talk about worlds is the point at which we really have sort of separate autonomous strands of physical reality. And that normally happens when things get large enough that these quantum interference effects become unobservable because they're kind of just sort of dispersed over zillions of other particles. I mean, this is why my book is called The Emergent Multiverse. Quantum mechanics isn't a fundamental multiverse. Again, not like Lewis's picture. If you look at a sufficiently fine grain, you don't see the multiverse at all. You just see quantum mechanics.
And this is getting ahead of myself, but this divergence that comes when you get to a larger scale, this relates to decoherence theory.
That's right, yeah.
Okay, great. Well, before we move on, though, just to be quite explicit again about Everett's insight, you said that, or you wrote rather, that there are two components to the interpretation. There's a contingent physical postulate, and then there is an a priori claim. Could we just lay those two out on the table?
So the contingent thing is the physics we have. It's the dynamics of our world is in fact a dynamics whereby at the fundamental level, things simultaneously coexist with many properties. And at the emergent level, the world separates into kind of largely non-interacting layers, each of which looks autonomously like ordinary definite goings on. That didn't need to be true. That's a contingent fact about the way our world is structured. There's then an a priori claim about the way we understand the relation between higher level and lower level ontology and the way in which we understand physical theories at all. And that claim would be that if I've got a claim about the world being structured in a certain way, that's all the work I need to do to justify the fact that the world is that certain way at a higher level. So all I need to do to justify my language of worlds here is to say that the mathematics of the theory is simultaneously instantiating multiple world-like goings on. There are philosophers and metaphysicians who want to say, no, you have a stronger obligation than that. You have to say, for instance, that all of our understanding of the world must supervene on some distribution of fundamental things in space and time, and that the world can only be such a distribution. You might have a view that somehow it's a priori necessary, that the perspective of the observer is playing a key role, which is not in the structure. There are lots of different routes by which one might diverge in one's philosophy of scientific interpretation. But that, in a certain sense, is not the kind of thing that could be different given different empirical possibilities.
Some of the problems that much better educated philosophers and physicists than I have with the many worlds theory that we'll get to later, largely psychological, are what preclude my fully buying into the theory. But one of the most powerful points in Everett's favor, from my perspective, is just how it really follows to a T quantum theory.
Exactly. Yes.
Yeah.
Yes, we have we have, I think, very good reasons for being scientific realists and thinking that our scientific theories are in the business of giving us objective third-party descriptions of the world. I mean, there are quite good a priori reasons you might think that, but also just if you look at science generally, that's what's in the business of doing. I mean, in the wake of quantum theory in the 1930s, people like Niels Bohr speculated that the whole of science would be rewritten to accept this sort of new perspective on things, but it hasn't been, in fact. The kind of third-party, humans are just more physics, humans just do physicsy stuff, the world gets on with things, that picture of science is just reigns effectively. So the case for scientific realism is awfully strong, and the case for the formalism of quantum mechanics is awfully strong. It's by a huge chalk the most predictively successful theory in human history. It's descriptive all the way up to why the galaxies across the night sky have the structure they have, all the way down to the Higgs boson. It underlies everything that we're doing, really, from computers, nuclear weapons, for better or worse, everything we know about the nature of matter. It's just an extraordinarily successful scientific theory, and trying to change that theory to resolve a philosophical problem is a very high-stakes move. It's kind of telling that the people who want to change philosophy and move away from scientific realism are usually physicists, and the people who want to change physics and alter the equations are usually philosophers. And there are exceptions in both schools, but by and large, you worry that sometimes people don't realize just how large a task it is either to rethink the whole way we think about scientific theories or to redo the mathematical core of quantum mechanics. And so the huge attraction of Everett to me, and this is a bizarre thing to say about a theory that posits parallel universes, is how extremely conservative it is, both as physics and as philosophy.
Mm-hmm. I think it's also an important point in favor of quantum mechanics that you didn't mention, that the two leading theories of quantum gravity, so string theory and loop quantum gravity, are both fundamentally quantum mechanical.
Yes, no, that's right. The only thing I'd say back to that is if I wanted to make the case for, say, Bohmian hidden variable theories or dynamical collapse theories, I'd say, well, the reason our fundamental theories of quantum gravity are unitary quantum theories isn't that we've got a ton of evidence that's true. It's that the people developing them don't take the measurement problem seriously, and so they've tried to extrapolate unmodified quantum mechanics into the realm of quantum gravity rather than trying to solve the measurement problem and then try to do quantum gravity with the modified theory. I'm not hugely moved by that argument, but it's not a foolish argument. There's some case to be made there. I mean, there's a variant of your point which I think has more power, which is to say, you might imagine as of 1930, when mostly we just had the non-relativistic starting point of quantum mechanics, then you might think that we didn't know how widely quantum mechanics was going to be applied. And then we had 50 amazingly successful years applying quantum mechanics all over the place, and all the time and all the place, the thing we were applying was the unmodified quantum mechanics, and attempts to explain anything novel by using modifications or supplementations of quantum mechanics got us precisely nowhere.